Okay, good morning, everyone. We have today the defense of the master thesis by Pau Esteva. The supervisors are Jose Ramasco and Master Zanin. Please go ahead, 20-25 minutes, no more.
Okay, so good morning, everyone, and thank you all of you for being here. I'm Pau Esteva, and today I'm presenting the master thesis called Analysis of the European Error Network, Properties, Evolution, and Resilience. This work has been supervised by Jose Javier Ramasco and Massimiliano Zanin. So through this presentation, I will start by introducing the topic, and then we are going to discuss how we applied complex networks to analyze the European Error Network. In the results sections, we are going to see first the evolution and the topology of the network, and secondly, an analysis of the vulnerability of the system. And finally, I will conclude the presentation with the main conclusions. So according to the International Air Transport Association, around 4.5 billion trips took place in 2019. So air transport is a complex system of huge economic and social impact. We have analyzed this system using the complex network framework in a similar way to how this has been used in other transport networks. These allow us to disregard about individual details and put the focus on the global properties of the system. So regarding air transport, through the literature, different representations has been used to model these kind of systems. The most popular one is that of airport networks, but there are other possible alternatives, like the one we are going to see here, of the structure of networks that regulate flight trajectories. So now let me further discuss the differences between these both representations. First of all, we have the typical airport network where nodes correspond to airport and a link connects to nodes whenever a direct flight goes between airport 1 and 2. Like, for example, here we have this picture of two pairs of Spanish airports. And however, real flights do not always follow straight lines between the arrival and the departure and arrival nodes, but they are instead restricted to follow what are called airways. These airways play a similar role to what happens with cars traveling along roads. And these airways can be seen as sequences of waypoints, here plotted in the figure with blue circles, which are navigational markers of specific coordinates, and they can also correspond to ground-based equipment that guide aircraft using radio signals. We have analyzed this structure of waypoints and airways, and the main purpose of this structure is to ensure safe distance between aircraft. So through the literature, we have detected a lack of interest to analyze this kind of systems because there is the general belief that it's a static entity where changes seldom happen. This was explicitly stated in this work by Sun and coworkers. So the main question we are addressing in this presentation is the root network a static or a dynamic system? So the main objectives of the present work are the following ones. First of all, to characterize the European Error Network as a complex network, identify its main properties, and compare them with other network representations. Secondly, to analyze the evolution of the system between 2015 and 2018, and determine whether this system is a static or a dynamic entity. And finally, we are going to also discuss the vulnerability of the system, identifying the most vulnerable parts of the network. So here we have a brief summary of only a few articles studying the topology of airport networks, where we highlight that most of these networks present a long tail degree distributions with the presence of airport hubs. However, in the second representation, the one we are considering here, this long tail characteristic is lost, and the most common degree distribution found is an exponential like one. So the data used through this work has been retrieved from Eurocontrol Data Archive. The annual data of this database is divided into 13 IRAC cycles, and each IRAC cycle corresponds to a time window of 28 days used to synchronize all the operational changes in the route structure. In particular, we have used 4 particular months or IRAC cycles corresponding to each of the years, giving rise to a total of 16 IRAC cycles analyzed. For each one of them, we have retrieved first the root structure, the network corresponding of where waypoints and airways we have seen previously. And secondly, we have also analyzed the flight trajectories that operated over this network. So as a final remark, let me mention that the network resulting from the underlying root structure, here plotted with black lines, and the one resulting from flight trajectories might not be the same, since this second case, trajectories are subjected to possible deviations and they can form new links. So now let's start to analyze the results of the thesis. First of all, here you have a global picture of the European air route network, where first of all, we observe a higher density of nodes close to main airports, and also a higher density in the center of Europe. Regarding the size of the network, here we observe the total number of nodes as a function of time, and we observe a significant growth of around 28.5% in the size of the network. So at least in terms of size, the stationarity of the system cannot be taken for granted. Here in the next slide, I present the cumulative degree distribution. Notice that the y-axis is in a logarithmic scale. And we observe that the vast majority of nodes have only a few connections between 1 and 5. And this has a very intuitive explanation, since a node with a large number of connections may lead to possible flight conflicts. We observe this kind of exponential-like decay in the degree distribution, which is completely at odds with what happens in most airport networks. Here in the bottom figure, I plotted the clustering coefficient and the average path length of, first of all, our results in red, and the results corresponding to table 1 and table 2 from the bibliographic results we have seen previously. We observe how the different representations fall in very different zones of the diagram, and how our results resemble the ones of the Chinese air route network. So to further discuss the evolution of the network, let's see the evolution of these 8 topological metrics. We have already seen the growth in size, but it turns out that the total number of edges didn't grow at the same rate, leading to a decrease in the density. So the network became larger and sparser. Regarding the mean degree, this value takes values around 3.5 or 3.6, which are much smaller than the typical values obtained in airport networks, like the one here reported from reference 15. In order to analyze the clustering coefficient and the efficiency, we used the normalized quantities by considering an average of 1,000 random networks. And first of all, we observe an increase in the clustering coefficient, meaning that the inclusion of new links have favored the formation of triangles. And secondly, a significant reduction in the efficiency of the network around 2017. Finally, we have also analyzed the assortativity and the modularity of the network by using the Logain algorithm. The modularity of the network has increased during this time period, favoring the inclusion of new nodes to the modular structure of the network. So overall, we see significant topological changes in the network. Let me mention that in the thesis, there's a further discussion about the information content of the network that I haven't introduced in the presentation, but we can comment it later if you wish. Here in the next slide, I present 2 maps with the most central nodes. First of all, we have nodes of highest degree that they are mainly located in close to main airports where a lot of airways converge. And secondly, I also present the nodes with highest between-us centrality that are located in key regions, like for example, this one here of the English Channel that connects the continental European airspace with the United Kingdom. So now we have discussed the topology of the network. Let's analyze now the flight trajectories that operated over it. First of all, and plotting the number of trajectories as a function of time, we observe strong seasonal oscillations with more flight trajectories in summer than in winter. And what we did is to, using the same waypoints as before, now consider the network whose links correspond to real flights that went between 2 waypoints here plotted in this little diagram with the red line. Analyzing the size of these resulting networks from planet and the executed trajectories, we can observe the following observations. First of all, in this plot here, we observe that there's a significant amount of redundant waypoints that remain unused. Secondly, and by looking at the total number of edges with the red and the blue curves, we observe that the number of connections is more than those encoded in the prefixed airways. And this is explained by the fact that actual trajectories are subjected to possible deviations, as I mentioned earlier. And finally, most of the links were used in a single direction. So when one analyzes this kind of system, it's important to take into account whether you are considering the underlying route structure we have seen before, or the flight trajectories operating over the system. And finally, to conclude with the analysis of the topology of the network, let me introduce you a set of evolutionary models we have used, whose main objective is to predict the added and the deleted links between consecutive ARC cycles. The best model is expected to have the highest rate of successful predictions, and the algorithm works as follows. It receives the graph to be updated and the total number of links to be modified. Then it assigns a score to each link based on different strategies that I will comment now. And finally, it outputs the n links with the highest score, the highest S. So we consider the link creation and the link deletion independently. And first of all, the first strategy used for deletion was to only keep the links used more frequently and eliminate the ones that remain unused. A second strategy that it also takes into account this rerouting quantity. As we can see here in this little diagram, this is the number of jumps needed to go between the extremes of the removed link after this link has been removed. And a third strategy that is quite similar to the second one, but it takes this quantity, this distance in nautical miles. And for the creation case, we limited ourselves to consider only the case of triadic closure, with the first strategy taking into account a reduction scores proportional to the reduction in distance, and a second strategy that also takes into account the number of lights crossing each triangle. So here I present the results as the number of positive coincidences as a function of the number of modified links. With different colors, I present the different strategies, and the black line corresponds to a complete random strategy. So first of all, we observe that the number of coincidences for deletion is much higher than those for creation, since the total number of unconnected pairs is much higher than the already existing links. Besides, the best strategies were strategy 3 for the deletion case and strategy 2 for the creation case, based respectively in using the rerouting distance and triadic closure. These both strategies obtain performances quite above the random null model, and they can even achieve close to or above the 90th percentile. So these results are suggesting that flight distance optimization takes an important role when we analyze the evolution of the network. And finally, in the second part of the results, let's discuss the effects of local and spatial disruption. And we are going to quantify the robustness of the network using this quantity, which I call rerouting cost. And now let me define how we obtain this. First of all, we retrieve the origin and destination pairs of all the flight trajectories of the dataset. And first, we assume that each flight takes the shortest path between the origin and the destination, here represented as G. Then we remove the link or the set of links we are studying, and we recompute the shortest path between the origin and the destination of the corresponding flight, here plotted as G prime. And we compute the difference, and we obtain the rerouting distance of the flight trajectory I. Integrating over all the flight trajectories of an entire IRAC cycle, we obtain the capital D, which represents the global rerouting effect of eliminating or deactivating a set of links. So resilient regions will tend to present more alternative routes and therefore lower rerouting costs. Here in this map, I present with the red color the most vulnerable links. First of all, we observe that they are mostly located close to major airports, as the case of London, Paris, or Oslo. And they can also be part of main transnational airways, as the case here plotted with the black arrows. Regarding different national airspaces, we observe that most of the most vulnerable links tend to fall in central and western countries, but there are some exceptions, like the case of Germany, which, in spite of being one of the countries handling more air traffic, it's more decentralized and dense route structure make it easier to find alternative routes. So overall, we haven't observed a clear trend between the rerouting cost of each link and the number of flights operating over it, as we plot here in this scatter plot above. And in order to compare different IRAC cycles with different number of trajectories, we used this normalized quantity by dividing by the total number of distance flown over an IRAC cycle. And in the first figure, with the yellow line, we observed that the percentage of most vulnerable links remained relatively stable, suggesting that there's a lack of improvement of the most sensitive parts of the network through this time period. Secondly, in the second picture, with the blue circles, we represent the mean rerouting distance per link. We observe how this quantity presents seasonal oscillations with peaks falling in, coinciding with the winter months. So the results are suggesting that summer months tends to be more robust on average, and that flights use more resilient parts of the network during the summer than in the winter. And finally, let's consider now what happens if instead of deactivating a single link, we deactivate all the links falling inside a specific region. And here I plot different vulnerability intervals with different colors. The most vulnerable regions, plotted with red, are located mostly in central and western countries. And again, we observe that some key regions, as the English Channel, present larger values for the vulnerability. As we have seen earlier, is also a region containing most of the higher betweenness nodes. With the white and blue numbers, we present the most increasing and most decreasing regions in terms of vulnerability. And we observe that, surprisingly, there are some regions presenting abrupt transitions in the vulnerability values around late 2016, early 2017. So with this, I conclude the presentation, but before I will give the main conclusions of the work. First of all, the European error network has been found to have a lower clustering coefficient and a larger average path length than most airport networks, and its degree distribution resembles an exponential one. Secondly, we have answered the question of whether this system is a static or a dynamic one by seeing that there's a remarkable growth in size and significant changes in the topology of the network. And regarding the vulnerability of the system, we have studied the case of local disruption, then can be a realistic approach of what could happen, for example, in cases of weather-related phenomena. And we have seen that most of the most vulnerable parts are located mostly in central and western countries. And finally, by analyzing this quantity, the average link vulnerability, we have seen that it presents seasonal oscillations with actual flights using more resilient parts of the network in summer than in the winter season. And that's all from my part. Thank you so much for your attention, and I'd be happy to start with the discussion section.
Thank you for the presentation. So we go now ahead with questions. Sandro?